So my name is Jurgen Gruber, coming from Austria. I'm also a civil engineer. I wanted to make the joke that I feel already very old, but I'm the youngest here on the stage so far. My experience in geosynthetic engineering is 23 years. Sounds long, but it's nothing compared to the speakers before, honestly. What do I want to talk about today? I want to give you an overview, and really just an overview of comparable life cycle assessments in and around roads. And I want to do that on behalf of the EHM. So you see I'm working for the company Solmax, but I'm also board member of the EHM. The EHM is the European Association of Geosynthetic Product Manufacturers. We have 23 members, and we are meeting together to create the voice of the industry. And the voice of the industry for geosynthetics is very much important because it talks about sustainability. It talks about those benefits we have with our materials compared to all the other construction materials which are under use. And to show that, we as EHM made life cycle assessments for different kind of cases where we compared our geosynthetic products with construction materials which also can be used for the same kind of functionality for different applications. We did 6 different cases. You see them listed over here. I'm going to talk about 3 of them, about filtration, foundation stabilized roads, and about a temporary road, which we did recently and we published last year at Eurogeo. And my colleague in the board of EHM, Henning Ehrenberg, will talk about landfills, about a retaining structure comparison, and about a filter function comparison in river construction, so in water management. That is what we as EHM undertook over the last years. We commissioned the ETH Zurich for that, so a body which is not directly linked to a manufacturer, so that we have a clear kind of a notified body behind it, and the ESU Services Limited to quantify environmental performance indicators and compare it to other construction materials. So what is a life cycle assessment? Wim already showed you this table which is used here in the Netherlands to compare the environmental costs. I want to show it a little bit more tangible in terms of the scope it has, this holistic view of all the emissions, all the environmental impacts, the production of, or the creation of products and its use and structures has, and then further on from the extraction to the production of the products, going into a structure, into a construction structure, and then also having in the scope the use of the construction structure, its maintenance, its services, till the end of the service lifetime of the construction, and then what happens with the products at the end. Do they go to the landfill? Are they recycled, reused? Are they going to the incineration? All of that is analyzed, quantified, and compared between different products, between different types of constructions. Why do we need such kind of comparisons? We already heard about it. We heard about climate change. We heard about global warming. We heard about CO2 emission goals of the European Union. Why is that important? We all speak about global warming, and we all speak about the consequences of those global warmings. And I will not go point by point with this illustration, which you see in my back. But when I came to that place here, in front of that building 23, I saw an insect hotel, which is quite popular for biodiversity, and everybody's doing that. And I'm going to tell you something. The global warming can't be stopped. We know that the global warming will be at least 1.5 degrees Celsius. 1.5 degrees Celsius means for this insect hotel that it is less occupied by 6% with that warming. If that warming goes from 1.5 to 2 degrees Celsius, so just half a degree more, it means that 3 times less insect species will exist. So that insect hotel will be quite empty in the near future. And that is what CO2 emission will create. That is what we have to work against as much as possible. So it is important as an emitter with construction to know exactly how much can we save, how much can we do for our environment, how sustainable can we build in the future without losing the functionality of our constructions. So the study, coming back to the LCA studies from the EHEM, the studies were based on ISO 14040. That gives the framework of life cycle assessments. And then more in detail, the ISO 14044, that gives you the specifics on what you're looking into. We are looking into 8 impact category indicators. The 2 most obvious are the energy you use along the way of a construction and its products and its extraction and its after service life. So the cumulated energy demand split into renewable energy demand, non-renewable energy demand. We are looking into the global warming potential. That is the CO2 emission or the CO2 equivalent emission. That is one-on-one the global warming indicator for us. And then we're looking into other categories and their indicators. The photochemical oxidation, we know it under summer smoke. Everybody who's living in a bigger city knows about that in the summer period when you don't see the next building. We are looking into particulate matter. That is something which directly goes on health and well-being for humans. We're looking into acidification and eutrophication, and we're looking into land competition, which is quite important, especially in the Netherlands. You don't have a lot of land to build on, so land competition is an important aspect, as well as the use of water for the full process we are going through. In terms of these LCAs, which we undertook as EHM, we built 3 bigger blocks. The first big block is the one where we can contribute a lot as a geosynthetic industry, from the raw material extraction over the production of geotextiles and geosynthetics and other building material production. We spoke about MKE. In general, we're speaking about EPDs, environmental product declarations. So we know for our products as geosynthetic manufacturers quite well what the CO2 emission is of that. So we have those kind of certificates on our products, and those kind of calculations are directly going into the quantification during an LCA. That is the product-related side. Then we are going into the construction-related side. Which kind of emissions do we gonna see during the construction and later on in the use of the construction, in the maintenance, and in the service of the construction? And the third block then is, what are we doing with the products after service life? Do we bring them on landfill? Do we bring them to incineration, which is quite popular for geosynthetics, to at least gain energy out of it? Or, as we have seen already, can we recycle and reuse our materials or the construction materials for other products at the end or for one and the same product? So Wim showed an example where, especially in the Netherlands, there was a process chain done where a geosynthetic was used after service life, repelletized and reused again for one and the same product. So that is what then gives the full quantification of life cycle analysis or assessment. Good. When we are sticking with roads for this kind of LCAs, we are sticking with a certain kind of functionality related to geosynthetics. I don't want to make it too complicated and too broad. Mainly we are speaking about separation and filtration with geotextiles, which means that, and you will see that we in roads have different mineral aggregate layers. Each aggregate layer has a certain functionality, and we need to make sure that there is no interaction and particle diffusion between different layers of minerals, so we need to separate in between. But at the same time, we also want to have pore water going through the filter layers or storm water going into the underground, into the subgrade. So the filtration and the separation are always 2 functions which are working together with each other. That is one part. The other part, we will speak about stabilization, so giving the soil or giving the road an extra kick, an extra mechanical kick to make it more rigid, more stiff, more functional, less deformable, and by that increasing the serviceability lifetime of the road or guaranteeing it. So those are the two or three functions which a geosynthetic will bring in these structures I'm going to show you. So let's come to the first LCA which we did. It was on filter systems in roads. So as said before, a filter system should take care of that water can, without building pressure, can pass through the mineral layers on one hand, can be drained into a drainage construction and then be drained off the earthworks. We all know that water is always the enemy of earthworks, of soil mechanics, so that is what we have to take care of. And on the other hand, we also need a filter stability in terms of separation. So we did a comparison of two structures which have exactly the same functionality. So we are looking into a paved road. The superstructure of the road is the same for both cases, but in case one, which is the upper picture you see, we are using a 30 centimeter filter layer made of minerals. And in the second case, which is the lower picture, we are using a geosynthetic or a geotextile separator and filter. Good thing about the EHM is we have 23 members and everybody can give his kind of what would be the best product to be used. And we are then taking an average on the material, which is selected by their own members, by all the members. And we are looking in a kind of a worst case scenario in terms of what we're gonna use to have the lower end of the comparison and not the more favorable end of those kind of comparisons. So in this case, we selected 175 gram per square meter geotextile versus the comparative LCA of 30 centimeters of mineral filter layer. They have the same boundary conditions. We're speaking about a lifetime of the road of 30 years, but this kind of construction also can survive 120 years. That was just one of the indicators. And when we're talking about filter layers, we're talking about permeability. In that case, we chose a permeability of 0.1 by the power of -3 meters per second. That is a typical permeability for a gravel layer, I would say, and a typical filter layer of geotextile. The drainage trench was also part of the full calculation. With the geotextile filter layer, you can reduce a little bit the dimension of the French drain, which was used there, gives a little bit of a benefit, not too important for the full case. What is important and where is the big difference between case one, the filter layer with minerals, versus the filter layer with the geosynthetic? You see case one, you see case two. The difference, if you look on 1 square meter of functional area for that filter layer, is clearly in the transportation. So you have to imagine for 1,000 square meter of functional area, you can use one roll of a geotextile, which is 6 meter long, 50 centimeter in diameter. This is what you have to bring to the construction site, and that covers this 1,000 square meters of functional filtration layer. If you compare it with 30 centimeters of gravel, over that 1,000 square meters of area, you're gonna speak at least about 30 trucks, which have to go from the lorry to the construction site, right? So you already see that is the big difference for our environmental cost indicator. If you want to have it like that, it is the big differentiator for this LCA study. Additionally to that, particulate emission is of course something which you have when you're working with a lot of gravel. Those is giving the differences. So I want to show you now for this different indicators which I showed you at the beginning. Not necessarily every value described, but just from a scale point of view, you see how much benefit there is in using a geotextile versus using this kind of mineral filter layer. On the left-hand side, you see category by category the case A, and you see the green color is the gravel, the production under apostrophe of the gravel, and the blue beam is the transportation, and that makes the big difference if you calculate those indicators category by category. On the other hand, this small black boxes, those is the geosynthetic part in it as the B version, and you always see there is a magnitude of difference between the different categories. And that's summarized, and I will not bother you with this kind of details with the other two cases, but that kind of thing leads to those kind of very impressive figures in terms of reduction or saving of sustainable indicators. So what we saw in that case study or in that LCA study was we have a lower environmental impact for all our indicators, at least with 75%. So speaking about 25% geosynthetic case versus the other case. We have at least 85% reduction on non-renewable cumulative energy demand over the full life cycle analysis. And in terms of CO2 emission, we are on less than 10% with geotextile filters versus a mineral filter. So that is quite impressive figures, which you see especially in this case, which was undertaken. Second part, we spoke about filtration and separation, but we also have this big benefit of the high modulus of geosynthetics, which is also bringing the advantage of uptaking shear stresses from the soil and creating a kind of a tension member in a road, which helps to reduce deformation and to save aggregate in your roads. So the second case which I want to introduce you is foundation stabilization by using a geogrid versus not using a geosynthetic. That case was based on a road class 3 semi-finished surface. So it's again a permanent road, a paved road. Foundation assumed to be 30 years service lifetime. The binder course 30 years and the asphalt layers 15 years. So a typical road, I would say. And we are looking into 3 basic foundation cases which were investigated. Something where you use a mineral aggregate layer and you increase the depth of that or the height of that to bring the stresses from the traffic into your subgrade without deformation. Case number 2 is with a geogrid layer inside to uptake the shear stresses and stabilize the soil and stabilize the structure. And a very popular way also to stabilize roads is by using hydraulic binders, cement or lime binders, which you mix into the soil and you more or less create kind of a stiff plate where stresses then are uptaken. From a dimensional point of view, case A, where you don't use anything, just mineral layers, you need an aggregate layer with 87 centimeters to have this class 3 road. Case number 2 with the geogrid is calculated to have 53 centimeters of aggregate. So you again see the saving in aggregate layer, which makes the difference then in the LCA study and then the quantification. And case number 3, the chemical stabilized or hydraulic stabilized soil, you stabilize with a mix in place kind of technique, 25 centimeters of existing soil to create this kind of a plate, a float plate, and then you fill additionally 32 centimeters of aggregate on it, and that is the road you want to have to stabilize your pavement. Here I jump immediately to the CO2 equivalent indicator. We are looking on the full road construction. In the full road construction, the saving of a geogrid reinforced road versus the conventional one is 11%. If we are looking on 1 kilometer of road, we are speaking about 80 tons of saving of CO2 equivalent emission with a geogrid reinforced layer. Compared to a chemically stabilized road, it is a saving of 30%, or saving is the right word, saving of 30% of CO2 equivalent emission. What does that mean in this case study? And you can read that all when you're going to the EHM website. You find the full study with all the details over there. We see lower impacts in all our categories for the geogrid reinforced case versus the conventional road. Lower climate change impacts compared to lime or cement stabilization. You saw that 30%. If you bring that into figures, we're going to see that we are saving around 800 tons on 10 kilometers of road versus the conventional study, which is in a tangible way 3,200,000 kilometers in a fossil-driven car, 80 trips around the world. Maybe that is something which is helping in the understanding of what you really can save by that. If you compare it with the hydraulic binder road, then we speak about a multiplicator of even 4 times that. This is the saving in that case by using a geogrid. Good. That case brought us to the last case, which was published a year ago, as said before, at EuroGeo, a temporary road construction, because we see that more and more, and we see that also as a very environmental friendly way of building roads, not just because of the indicators, also because of the rebuilding, recultivation of a road. What you see in those two pictures is twice multifunctional geosynthetic products. On the left-hand side, a geowoven product made of polypropylene. On the right-hand side, a non-woven product where a geogrid is attached on to give the functionality of separation, filtration, and reinforcement. So both possibilities are given, also with polypropylene in that case. The important thing is, if you make this kind of temporary roads, you want to recultivate it afterwards. You want to make the landscape as it was before the construction. For instance, in the energy sector, when you're building access roads for your wind farms, you need that for a temporary use, and then you rebuild it. We heard the same example on TenneT. To bring some energy infrastructure into the soil, you use this kind of access roads for heavy loading, and after the pipes are in or the cables are in, you want to remove the full thing again. So what is the benefit of that? The benefit of that you build that on a green grass, so you don't remove anything. You lay down your geosynthetic, you put your aggregate on top to the certain height level you need to bring the traffic forces down to the underground, down to the subgrade without too much deformation. And when the construction work is done, you remove everything. You can take the gravel again, you can reuse it, and you can take the geosynthetic again, and in best case, you can repelletize it and reuse that in your production again. So that is the idea behind this temporary roads with geosynthetic stabilization. What have we looked at that case? We've looked at a subbase, and we can design that, we can calculate that. A comparison between non-reinforced versus reinforced case. The non-reinforced case needed in that case 55 centimeters of aggregate thickness, with the reinforced case 35, so 64% of aggregate. We looked from a producer point of view into different geosynthetic solutions. You have seen a woven polypropylene, but we also looked into this composite materials, a non-woven filter layer plus a geogrid, which is giving the stabilization. And we also looked into a polypropylene non-woven with a reinforcement on it made of polyester. Those things were in our calculation. We used then the worst case of those three materials. That was then a product with an average weight of 360 grams per square meter for this temporary road with a service lifetime of 2 years in our calculation. So that is just what I told you. Unreinforced case versus reinforced case. You see the saving of aggregate of around 35%, 36%. That is not the limit. We know that we can reduce by 50%, but we wanted to go the safe way, I would say, for that kind of example. You also see a design parameter CBR of 1.5%. That is something which is typically, I think we see that in our daily practices, that we are on swampy areas, and then you find this kind of subgrade layers where you find a lot of water in it, where you find a lot of compression in it. So you need to stabilize in a certain way to let your traffic flow smoothly through the access road. What we also did with the other cases, I didn't show it there because it would be too much detail, is also that we always did kind of sensitivity analysis. If you make an LCA, you have to have certain kind of assumptions. Those assumptions are data-based normally, but of course we also want to see how much impact is, for instance, if a lorry is not 50 kilometers away from the construction site, but 100 kilometers or just 20 kilometers. So what does that mean for the full study? We also looked into what are you doing after service life? Do you have the incineration facility? What have you used? Can't remember. 20 kilometers away, 100 kilometers away. In that case, we used 100 kilometers. And what is the distance for supplying the materials on site? So that sensitivity analysis is always in the back of those studies to see where is the big influence in the environmental indicators. What we had in the LCA 6, in case number 6, is also the part of deconstruction. So that was the first case where we said it's temporary, we deconstruct, we take the deconstruction also in our indication and quantify it. and that was done for this temporary road case. Important to say here is that we did not take all the benefits. I explained the benefits of having those kind of access roads and rebuild them and reuse the materials there. That was not taken into consideration, this kind of reuse. So we calculated here with an incineration facility, I told you before, with 100 kilometers from the location, or bringing the material to the landfill site, which was 50 kilometers away, or 20 and 50. We calculated that there needs to be a certain kind of a process of washing geosynthetics before you can incinerate them. We heard before there is also the potential that you can fully recycle it, then you need more in the process. So there is more demand in washing, in cleaning, in shreddering, baling, and then bringing it back to the pellets you can use. But that is not part of that calculation, or was not part of that calculation. For the next one, we can use also this kind of scenarios with the benefits out of it. What was the results of that case? So here again, the most important indicators. Resource used was on, I think, 64%. Cumulative energy demand was on 70-something%, and the carbon footprint also below 80% of the case without the geosynthetics. So also here you see a significant reduction of environmental indicators for the temporary road case. Yeah, so the summary of that road case is the same as we saw with the other ones, a lower impact compared to conventional construction methods. We talked about it. What I want to say here, and not repeat again, is I didn't look, or we looked with that case studies into the environmental impact. But we also did a study afterwards on the economical impact of those cases versus the conventional cases. And I think, Henning, you have that in your slides later on. I just want to say for this temporary road, where we see a significance of a reduction of 20+% on environmental indicators, if you calculate that through from an economical point of view, we also speak about a saving of 30% plus by using less aggregate. So also that needs to be somehow in our mind when we're looking into these LCAs. Good. I will not do a summary or a wrap-up. That is in the slides of Henning with his presentation, but what I want to link you to is the EHM homepage, ehm.eu. You find all that LCA studies with the full reports, with all the full details on it. Use it, be an ambassador, because we see that with this kind of construction material, we really can do something good for that world. And I think you, especially in the Netherlands, see that even with clearer eyes than the rest of Europe sees that. So you find those LCAs there, you find the presentations there. We have it there publicly available so that everybody can use it and be an ambassador for that very good thing we're going to do together. Thank you very much.